Students, welcome back to the part 2 of lecture number 37, and we have discussed about the errors. Let us talk a little bit about the model score. In machine learning, one of the main tasks is to model the data and predict the output using various algorithms. Since we are using many algorithms, it is always difficult to choose which one is predicting the data better way, and we need to compare the models, which we will do that. And how do you choose? One is the error, which one is giving least error, other one is the score, model score. So F1 score is one such very important score. F1 score is a metric used to evaluate performance of any machine learning model, and it combines two parameters, one is called precision, other is called recall. We will discuss about these two. F1 score is very important, that is why, because it allows you to understand, evaluate the performance of the model by combining these two things, and it is calculated as a harmonic mean of precision recall. All of you know geometric mean, arithmetic mean, harmonic mean. This is a harmonic mean. It is a harmonic mean of precision and recall. A harmonic mean is a type of average calculated by summing the reciprocal of each value in a data set and then dividing the number of values in the data set by this sum. So basically you take a reciprocal of each value in a data set and divide the number of values in the data set by the sum. That is what it is. So value of F1 will be between 0 and 1, and 1 is better than this. So what is precision, by the way? Precision represents the accuracy of positive predictions. It is accuracy of the positive predictions. So you can have in a model, you can have positive prediction, negative prediction, right? So you talk about positive predictions. So precision actually represents the accuracy of the positive predictions. It calculates how often the model predicts correctly the positive values. It is a number of true positive predictions divided by the total number of positive predictions. That is what it is. So precision is the, if I define TP as a two positives, AP as a false positives, TN as a two negatives, and AP as a false FN, so not AP, FN as a false negative, then precision is nothing but a true positive divided by total number of positive predictions, that is two positive plus false positive. You can predict both actually. So if you take an example, suppose you are modeling the occurrence of the cervical cancers and you have data from different patients. So now you have, when you predict and check whether predictions are correct, you can have true positive correctly predicting, you can also have false positive. Model has predicted, but actually it is found wrong. You can also have true negatives, like you predicted that it will not happen, cervical cancer is not happen, and actually is found also not happening. And you can also have false negative, like you predicted it will happen, so you predict it not happen, but actually it happened. That is called false negative. So true positive means predictions and the actual things are both matched, both are correct. False positive means predictions says no, not happen, cervical cancer will not happen, but actually it happened. That is called false positives. Okay? And then true negatives are obviously prediction also no, actually also no. False negatives, prediction says yes and actually it did not happen. That is what is called false negative. So precision is defined as that. It is basically it tells you how often the model predicts correctly the positive values. It is basically number of positives, true positives divided by total number of positives, true and negative positive, positive all positives. So if there can be 10 positive cases and 5 negative cases, the model can identify 5 positive cases properly, but out of these 5 identified cases, 4 positive cases are actually real positives and 1 is negative. So therefore precision is 80%, 4 by 5, right? Total 5 cases, 1 and 4 are predicted correctly, so 4 by 5 is that. 1 is false negative, false positive. So what is recall? Well, recall represents how well a model can identify actual positive cases, how well it can. So it is a number of true positive predictions divided by total number of actual positive instances. So recall is nothing but total number of, basically is what? It is a number of true positive predictions, yes, and divided by total number of actual positive instances. So true positive and false negatives. It measures the ability of the model to compute the actually all positive instances. So, these two are important for you to understand what is precision and what is recall, right. That is what I have been repeating it again and again, and why I am repeating, because these are not easy to define always. That is the main problem of when you measure the predictions and recall. Please keep it in mind. Precision depends on the how many times actual prediction is positive, encompasses the total number of positive predictions. So, predictions can be either true positive or false positives. Similarly, negatives can be true negatives or false negatives, both are possible. So, recall actually takes care of negatives and precision takes care of positives, right. You can clearly see that. So, accuracy is nothing but what? Accuracy nothing but total true positive plus true negative divided total. That is what is called accuracy, right. But more than that, you can define F1 score. F1 score is nothing but this formula, precision into recall divided by precision plus recall, and this whole thing will be multiplied by 2. That is what is called F1 score. It is very difficult to understand, right. F1 score is basically harmonic mean. You can see that it is taking inverse of that, and that is why 2 comes into picture. So, talking about the examples of accuracy predictions for positive cases in a very high 80%. So, recall can be also low. So, F1 is basically talking about that. Now, why we talk about harmonic mean, right? Why? Harmonic mean is basically equivalent to the arithmetic mean of reciprocals of the quantities. It is nothing but a, see, if I have quantities x1, x2, x3, harmonic means is what? 1 by x1 plus 1 by x2, 1 by x3. So, that is what is the reciprocal, they are reciprocals, and now we can take a mean of that, mean of the reciprocals. That is what is called harmonic mean. In actual cases, arithmetic mean, if I consider arithmetic mean of this, is nothing but x1 plus x2 plus x3 divided by 3, right. Harmonic mean is basically what? 1 by x1 plus 1 by x2 plus 1 by x3 divided by, this is whole thing is divided by 1 by 3. That is what is called harmonic mean, right. So, we take harmonic mean because it provides reciprocals of the quantities that should be averaged by arithmetic value. More precisely, with the harmonic mean, you transform your numbers to the averageables forms. So, hope you understood everything. So, let me also tell again what is true positive and what is true false positive, true negative and false negative. True positive is the number of instances correctly predicted as positives by the model. False positive is number of instances incorrectly predicted as positives. So, that means model has predicted positive, but actually it is not positive. True negative means number of instances correctly predicted as negatives by the model as in actual cases. False negative again, number of instances incorrectly predicted as negatives by the model. Actually it is correct, but model predicted wrong, right. That is what is called false negative, and this is how we can measure this. Am I clear? So, that is basically about the different kinds of scores and other things, and most important is the precision and recall from their F1 score. There are many other scores, by the way. So, let us not talk about it and discuss. So, let us move into the material informatics aspects, and material informatics is a new subject which is coming up, and in fact, we are going to discuss about material informatics here, and we will discuss about little bit about that, about 3 to 4 lectures. But I want to first tell you that it is a new subject, and please read these papers, they are very important. I think this is 2005, not 205, yeah. So, most importantly by Krishna Rajan, he has written couple of good papers, and this one by Muhammad Hassan Mubarak in Applied Surface Science Advances. This is also a very good paper. Please read these papers. I will discuss many of these aspects from these papers only. So, what is material informatics? Well, it uses information science with computer science to improve the efficiency of material development. So, we started this subject or this particular course talking about the design and discovery of materials. And so, that means you want to design new materials with target set of properties, or you want to discover new materials with some exceptional properties. These are the two reasons why we use machine learning and deep learning. So, therefore, prediction property or target set of properties is very important, and in that case you need to do a lot of analysis of your data, and that is why informatics becomes very important. It uses information science, a lot of information, right. Information can lead to knowledge, knowledge can lead to discovery. So, the use of information science and computer science can provide us a platform to improve the efficiency of these, predicting or discovering new materials or design new materials with target set of properties. So, we are basically combining material science knowledge with informatics and data science. That is what is the basic aspects of this. And what is your target? Target is to discover new materials which can be used, deployable, and also design. It is basically effort to improve the efficiency of the material development. Why it is important? As you know, search for new alternative materials, whether through experiment or simulation, is very slow, by the way, and it takes almost 25 years to design, develop and understand the material for real application deployment. The material cycle is very, very long. So, if you want to do something very quick, next like 5 to 10 years time, how do you do it? That is why we need to do informatics. It is better to understand the underlying science which are governing the behavior of materials, and that is why informatics can help. It can allow us to analyze the trends of data on the basis of some predictions of the new materials. That is the key aspects of the material informatics. And the search of new materials is always difficult. That is what is the key aspects of that. And we have seen that the search of through materials by simulations or experiments has been a tough task. Although we have some experiences of discovering materials or accidentally, that I talked about it at the beginning of this course, but those are all very rare, rare aspects. But informatics is very widely used in biology, drug delivery and in astronomy, but we are very slow in using it material science. So, it should be used more of that. We need more systematic efforts to use informatics to discover and design new materials. So, give an example, when you combine with large combinatorial space of chemistries defined by even small portion of periodic table, okay, you know that. So, let us talk about that. If I take a small portion of periodic table, let us say if I take only this elements, okay, you can see 1, 2, 3, 4, 5, 6, 7, 8, 9. And if you want to make binary alloys, so it is basically NC2, 9C2, 9 into 8, 2 into 1, that is equal to 36 different combinations possible. Am I clear? So, if you want to do ternary alloys, 9 into 8 into 7, 3 into 2 into 1, it become 84. And if you do N9C4, it become 9 into 8 into 7 into 6 divided by 9, 4 into 3 into 2 into 1. So, 3 to 6, 6 into 3, 18 into 7, and that means what? 18 into 7 is 115. So, you can see the number of combinations are increasing rapidly from 36 to 84 to 115 for 9 elements. That is what happens. So, now if I ask the question, shall I check all these combinations in doing experiments, whether they are going to form materials which will satisfy my requirement. If I want to do that, let us say by experiments, it will take me couple of years. Even if you do by simulations, that will also take couple of years, because simulations also are not so fast. You need a very high fast supercomputers, which many of you may not have it. So, that is I am talking about only 9 elements of 108 elements of periodic table. Think about it. So, that is the challenge. Hence, the search for new materials to new applications limited to educated guesses. We material scientists are very good at it. We do a lot of educated guesses. So, data that does not exist is often limited to small regions of the computational space. Sorry, data that exist actually, that are mostly limited to small composition spaces. Experimental data is dispersed in the literature, and computational data is also limited to a few systems for which reliable data exists for calculations. Even after recent advances of the high speed computation, there are limits, there are also limits to how to the structure and properties of many of materials can be calculated. We do not know, actually, we may not have the atomic potential available for all the elements. Go back to a lecture by Professor Tarun Kundu on the MD simulations. That requires the atomic potentials, which may not be available for many systems. So, that is the main limitation. Hence, this poses both a challenge as well as opportunity for you. Challenge is to deal with extremely large disparate databases and large scale materials or large scale properties, large scale compositions. It is here this knowledge discovery is very important, and this is an interdisciplinary field of merging that ideas from statistics, machine learning, databases and parallel distributed computations. So, that is why we need to develop and scientific databases of materials. We also need to develop AI related technologies, and lastly advancements of the supercomputers. So, first and foremost thing is that we need huge material databases, then only we can apply our AI related technology like machine learning and deep learning to that, otherwise you cannot do that. But even if you do it, even if you use this deep learning machine learning tools, you need high computational power, mostly supercomputing performances. Without that you cannot achieve anything. So, the core of AI technology is based on the statistical mathematics called machine learning and deep learning, we have already discussed, right. So, if I have to put together how we are going to discuss, first we need to discuss what all the material science databases we have and what all we need to create, and then we need to discuss about it, how to use AI based technologies to extract information from the databases, and finally whether we can use supercomputers to do that. These three aspects are the basic backgrounds of the discussion. So, it is clear to you the material informatics is made up of theory of properties, experiments, simulations, databases, cloud computing and security. High performance supercomputers and large scale material databases are the need of the hour. Without that we cannot handle informatics, and it is very important considered by every countries in the world who are developing or develop. Like in US, it has spent almost $200 million to promote material informatics as part of material genome initiatives or MGI. Industry 4, the fourth industrial revolution, what is called, it is very common in China and Europe. So, Japan is also using that now. So, therefore, we need to move fast or catch up rather fast to these countries to understand how we can use material informatics more or substantially. That is the key aspects in which we will be discussing a lot in material informatics. Now, before we move ahead, let us first think about it whether we have enough data in material science or not. So, material informatics require data, right. So, as you understand that this without data you cannot do material informatics. So, where our databases are? So, material informatics, the real question we always ask, data feast or data famine? Do you understand that? Do you have a huge data or you have very less data? So, now in this connection let me tell you how do we define that we have a huge data. Let us talk about ceramics, structural ceramics. What is it? Structural ceramics has very important property called fracture toughness. Even for implant applications also fracture toughness is very important. You know, measuring fracture toughness is not an easy job. It takes a lot of efforts to measure fracture toughness of brittle materials, because the quality of data as we discussed in the last lecture is very important. So, therefore, here you do not need large amount of data, you cannot get actually large amount of data, and you cannot calculate also using computational tools the fracture toughness easily. Reliability is a big problem there. So, measurement reliability as well as computational reliability both a challenge, even to get 5 or 10 data points. They are the biggest challenge if you want to generate database of fracture toughness with structural ceramics, and without database you cannot do material informatics. Hope you understand that. So, data, that is what we call data fist or data famine. So, but that is not the case for, let us talk about tensile testing of steel samples. We know that steel samples, steel has different kinds of steel sample exist, and many people across the globe has done lot of tensile test. We have huge amount of data, and that database is useful, that can be used for material informatics. Okay. There we do not have feast of data, by the way, for this kind of situation, but at least we have sufficient data. So, in this connection, let me tell you, in material science there are two types of databases we use, two categories of data sets we use, which are very famous. Two types of databases or databases we use, two types of. One is called material property databases, you know there is this book called Smithel's Handbook of Material Property. There are many other handbooks, I am just giving an example. Material property, I mean both mechanical and functional properties. Mechanical properties mean strength, ductility, fracture toughness. Functional properties mean thermal conductivity, electrical conductivity, and many others. And then you have thermochemistry databases. These are known as thermodynamic databases. Okay. These two types of databases are very common in material science. So, one is related to the mechanical or physical properties, another one is that is called material property databases, second is the thermodynamic databases or thermochemistry databases. Okay. So, now in material science community we also have another database, okay, that is called crystallographic database. We also have that, right. Crystallographic databases are also very widely used in material science community. But crystallographic databases or thermodynamic databases means what? Let me explain to it. Property you understand, mechanical or physical like density or something, or functional like thermal conductivity. Thermochemistry means thermodynamics databases. They are heat capacity, and what else it can be. Heat capacity is one important, and calorimetric, right. Crystallographic databases mean crystal structure. Okay. You know that there is a book called Pearson Handbook of Crystallographic Databases, that is also important. These three are the main informations available to us. Now, the question is, if you look at carefully the three, basically there are two databases, one the property databases and the thermochemistry databases. Why? Because thermodynamic databases also predict what kind of crystal structures are going to form when you do some processing. Okay, when you mix two materials, two elements, at what temperature, what pressure, what kind of phases will form, and phases are basically what? Crystal structure, that is what is the phase. So, therefore, in actual cases we combine the crystallography databases with the thermochemistry databases, and development of computationally phase diagrams are very common in our system. We always develop a lot of computational phase diagram calculations almost routinely nowadays, because these databases are available, and you can do it this calculation using a console. You do not need to do it using any kinds of softwares, and that gives you information about the crystallographic phases with some crystal structures. In fact, one can get the information of crystal structures by looking at the crystallographic databases of different common phase diagrams, right. So, these two are connected, remember, they are not independent databases as such. That is why you always say that in material science there are two definite databases available. One is called material property databases, other one is called thermochemistry databases. There is no other databases available to us. But before we moved into what kind of databases and what we can do, let me also tell you that long back there is one person called Michael Ashby from Cambridge University. He actually proposed some kind of a chart, Ashby map by his name. There he used to take all the material property data and cluster them. Take the material property of, let us say, strength versus tensile strength versus elastic constant, and you can make a two-dimensional plot and cluster different material, polymers, composites, metals, ceramics, you can cluster them. So, that is the first evidence of using of informatics in real life. He did it actually, and he did it very nicely. So, the next lecture we will start discussing from Ashby's map, how he has used this information and placed it so nicely that we can actually get a lot of insight out of it. Insight means we can actually take this informatics to design a material, select a material, apply it in actual case. That is what something we will discuss first. Then we will talk about what is that. That is the first thing, is material property related, and there he discussed all properties, physical, mechanical, and this. So, we will discuss on these aspects first in the next lecture. Second thing we will discuss about is the thermodynamic databases. We talked about CalFIRD already as part of our course, but I will show you how different kind of thermodynamic databases are available, how it can be used for material informatics. Thus will be the main theme of discussion for the next two lectures probably, and then we will talk about it, what are the way forward for material informatics. So, material informatics, as you understand, is a very important field of study, even it will be going to be more important than AIML, which you are learning now. How can you use material informatics to do all kinds of things? Okay, I talked about it. So, material informatics is consisting of materials theory, material processing, property measurements, computational techniques, characterization, atomistic modeling, continuum modeling, and this knowledge discovery in databases or data mining is an interdisciplinary field, which will with merging ideas from statistics, machine learning, databases, parallel and distributed computing, and this provides a unique tool to integrate scientific information and theory of material discovery. So, with this, let me stop here, and we will come back to it in a more detailed manner in the next lectures, so that you understand this very clearly. Thank you.